Hi to everyone. MEM School of Engineering, Department of Mechanical Engineering, Online Class 5, Subject Mechatronics, Unit 1, Chapter 5. Myself, Saravanan, Assistant Professor, Mechatronics. This is the course objective and outcome of Mechatronics, the syllabus, textbooks and reference, Unit 1. So in Unit 1, today we are going to see about Chapter 5, that is sensors and transducers. Okay, in this sensor and transducers, last class we discussed about LVDT, potentiometers, tactile, force, and incremental encoder sensor like that we discussed. We have more type of sensors like that. Okay, so today we are going to see about capacitance sensor, strain gauge sensor, eddy current sensor, and Hall effect sensor. Okay, these are topic we are going to discuss. Okay, let's see. Strain gauges. So strain gauge sensors. So the strain is an element, is a ratio of changing in length in the direction of applied load to the original length of element. The strain gauge changes the resistance R of the element. Therefore, we can say strain gauges. That is delta R divided by R is equal to G of epsilon. That is G is the constant of proportionally and is called gauge factor. In general, the value of G is considered between 2 to 4. The resistance are taken of the order of 100 ohm. That means change of resistance in the strain gauge element. Okay, that means so they are mold the metal. So you are small element, so length element, that is material, normal conductive material like that they are using spring like that they are fixed in the particular mold. Okay, if you are putting some weight on this mold, okay, the length of the wire will be increased. So when length of the wire will be increased means the resistance will be vary. So this sensing, this resistance and voltage variations calculated by the some bridge circuit. Okay, using these values we can calculate the weight. Okay, most of the washing machine they are using like this. Okay, if I identify the screw strengths, identify the weight of the cloth, total cloth, the weight of the some objects like that we can identify. So resistance strain gauge follows the principle of changing of its resistance as per the equation. It comprise a pattern of resistive foil arranged as shown in figure. So these foils are made of constant alloy and are bonded to a baking material. So we cannot use all the material as a strain gauge element. Okay, we need to use particular metal. Then only we can linearly check the weight variations. That is constant alloy they use it. Then plastic polymer like that they are using. These strain gauges are secured to the workspace by using epoxy. So cement extend 19910 SL. Okay. So the workspace undergoes changes in its shape due to external loading. The resistance of strain gauge element changes. The change in the resistance can be detected by using a Wheatstone resistance bridge as shown in the figure. Okay, so last diagram we sent some bridge circuit, that is Wheatstone resistance bridge. Okay, by using this formula R2 divided by R1 is equal to Rx divided by R3, we can calculate the resistance change, that is resistance variation. So application of strain gauges. So strain gauges are widely used in experimental stress analysis and diagnosis on machines and failure analysis. Okay, they are basically used for multi-axial stress testing, proof testing, residual stress and vibration measurement, then torque measurement, bending and deflection measurement, compression and tension measurement, and this strain measurement we can using strain gauges we can calculate, as well as strain gauges are primarily used as sensors for machine tools and safety in automotive. In particular, they are employed for force measurement in machine tools, hydraulic, pneumatic pressure, and is the impact sensors in aerospace vehicles. Next one is capacitive sensor. So capacitive sensor, it's a non-contact type sensor. Is primarily used to measure the linear displacement from few millimeters to hundreds of millimeters. It will identify distant displacement of few millimeters to up to 100 millimeters. It comprises of three plates with the upper pair forming one capacitor and the lower pair another. Okay, so one of the plates is moved by the displacement so that the plate separation changes. Area of overlap changes due to the displacement. Okay, this schematic of three plate capacitive element, sensor and a displacement measurement of a mechanical element connected to the plate 2. So this is the plate 1, plate 2, plate 3 model. So middle plate, plate 2 connected with the element. If element movements means the plate 2 will be movement. Okay, already we knew that the capacitor store the energy as a electrostatic energy. So the distance between the two plates will define the capacitance. If we change the distance between these two means it will change the capacitance in plate between plate 1 and plate 2 as well as plate 2 and plate 3. Using this we can calculate the capacitance. Using capacitance variations we can calculate the distance. Okay, that is displacement we can calculate. That is we have a formula C is equal to epsilon A divided by D. Okay, that is displacement measurement using capacitive element sensor. That is C is equal to epsilon R epsilon 0 A divided by D. That is C is a parallel plate capacitor. That is capacitance. Epsilon R is relative permittivity. So epsilon 0 is permittivity of free space. So A is the area of overlap between two plates, and D is the plate separation. This is an example for this is the formula for common capacitor. Okay, here we are using two capacitors, that is between plate 1 and 2 and plate 2 and 3. Okay, so as the central plate moves near to the top plate or bottom one due to the movement of the element, okay, for which displacement is to be measured. So separation in between the plate changes. This can give us C1 is equal to, so this formula epsilon R epsilon 0 A divided by D plus X, and C2 is equal to epsilon R epsilon 0 A divided by D minus X. Okay, so C1 and C2 are connected to the Wheatstone bridge. So then the resulting of balance voltage would be in proportional to displacement of X. Okay. Then applications of capacitive element sensor, feed hooper level monitoring, small vessel pump control, grease level monitoring, level control of liquids, metrology applications. Measure shape errors in the part being produced to analyze and optimize the rotation of spindles in various machine tools such as surface grinders, lathe, milling machines, and air bearings, spindles by measuring errors in the machine tools themselves. So assembly line testing,